Hello, this series of videos will be about linear programming, and I'm going to start with some fairly basic ideas. The idea of linear programming, of course, has to do with linear equations and linear inequalities, and so to start this off, I'm going to introduce graphing linear inequalities. So I'm going to start off with a linear inequality. I'm going to start off with 3x plus 2y less than or equal to 6. Now, a lot of times graphing intimidates people. Now, probably the easiest way to graph something that is in this format is to find the x-intercept and to find the y-intercept. And to find the x and y-intercepts, those are fairly easy to do. Consider that on the x-axis, all the y values are equal to 0. Because, and that's the case, because they are 0 units high or low above the axis. On the y-axis, on the other hand, the x values are 0. So an easy way to do this is to consider what happens when x is 0. And I'm going to pretend that this is an equation first for the sake of the graph. So what that effectively does is it makes the x term disappear, and all we have left is 2y equals 6, and then y will equal 3 when we divide both sides by 2. So the y-intercept is 3. We can do a similar thing with the to get the x-intercept. We make y equal to 0. And again, pretend it's an equation. The 2 times 0 just disappears, and we have 3x equals 6. We divide both sides by 3, we get x equals 2. So the x-intercept is 2. So we can mark those places on the y-axis, right there. That's where the y-intercept is, and here on the x-axis, that's where the x-intercept is. And we have 2 points, which means we can draw a line through them. Now what we can see a line roughly goes about right there. And since it is an inequality, that line is really a boundary. We are looking for what is less than or equal to that. When you think less than or equal to, you should think below. And if you're thinking below, put equals up there. If you're thinking below, then you should think of shading below that graph. So any region, any point in that region will satisfy that inequality. If you take an x and a y value in that region, then and you plug it into that inequality, you will find that it will be true. Now I'll go to another screen. Here is a composite or compound system of inequalities. I have x is less than or equal to 3 and x is greater than or equal to -1. Let's do the y greater than or equal to -1 first. These are, well, if it was y equals -1, that means no matter what x is, y always equals -1. It's always 1 below vertically, which means it is a horizontal line at y equals -1. Roughly like that. That's about as straight as I can draw it on this utility. And since it is greater than or equal to that, we will be shading above that. Now, I'm not going to shade just yet, because what we want to find is the region that is common to both of these inequalities. Let's consider x is less than or equal to 3. Well, if y equaling some constant, or with being greater than or equal to some constant, is a horizontal line, what would you suppose x being less than or equal to a constant would be? If you're thinking it is a vertical line, you are correct. It's going to be a vertical line at x equals positive 3. And I will draw that line now. So now we have our region sort of defined here. We have x is less than or equal to 3, which means it's everything to the left of 3 and above -1. So if I think about, this is all the stuff above y equals -1. This is all the stuff that is left of x is less than or equal to 3. Cross-hatch this best I can. And so that region there, of course it continues, but that's the region that we can see right now. Let's make these go all the way down to the y equals -1. So anything in that region will satisfy both inequalities. So what we're working towards is being able to define a region that is what is referred to as the feasible region. And I'll go to another graph to demonstrate what that looks like. So now I'm going to go to a new graph on a new screen. Okay, we now have 4 inequalities here, and we're going to consider all of them. X is greater than or equal to 0, y is greater than or equal to 0. Basically what that does is it restricts our region to positive x and y values. So I'm going to go ahead and draw the boundaries that are at the x and y axes. I'm going to draw it this way to show that it's just that first quadrant that we're looking in. Now we can look at our 2 more complicated inequalities. 2x plus 3y is less than or equal to 6. So let's first consider that one. The 2x plus 3y is less than or equal to 6. So if I make y equal to 0, I have 2x equals 6, which means we have an x-intercept at 3. If I make x equals 0, I have a y-intercept of 2. So I can do x equals 3, make a little point there, and a point at y equals 2, and then I can draw a line between them. Okay, so that takes care of that one, and it's going to be shaded below. So it's going to be this small region down here. Now I'm going to consider the other one. I'm going to do my work below this. If I make x equals 0 on my second inequality, I have y equals 6, which means I have a y-intercept of 6. If I make y equal to 0, I have 3x equals 6, or x equals 2. So my y-intercept is 6, my x-intercept is 2, so I just draw a line in between those 2 points. Okay, so that's my my fourth and last inequality. And we have, again, we're shading below this. So we've actually defined this bizarre little quadrilateral shaped region right in here. And that is basically what is considered our feasible region. Right in there is what's called the feasible region. That means that is the values that x and y can take on, and it satisfies all of these conditions. You can also consider these to be parameters. So all of these parameters are what need to be satisfied. Now we're going to look at a full-blown problem. I'm going to step through it very slowly. Please pause as you need to. There's going to be a lot of moving parts to this problem. We're going to try and put all this together. And I'm going to introduce a new idea of how to think about these kinds of things. But it works best when I have an example. So I'm going to give you an example. A real-life sort of situation, or close to real-life sort of situation. Earthquake victims in China need medical supplies and bottled water. Each medical kit measures 1 cubic foot and weighs 10 pounds. Each container of water is also 1 cubic foot and weighs 20 pounds. The plane can carry only 80,000 pounds with a total volume of 6,000 cubic feet. Each medical kit will aid 6 people, and each container of water will serve 10 people. How many of each should be sent in order to maximize the number of people aided? Now, this problem probably looks rather overwhelming to you, and understandably so. There are a lot of things to consider here, and it's not one that you could probably do in your head very readily. This is where the math of linear programming really can shine, and it can give us an idea how can we do this the best that we can. This is a place where linear inequalities are extremely practical. So I'm going to start by defining a few variables. I think that defining variables is the best place to start. And the question then is, what are our variables? How do we know what they are? The way to know what our variables is to look at the question that is being asked at the very end of this whole word problem. How many of each should be sent in order to maximize the number of people aided? Well, how many of what? What are we talking about here? Well, we are talking about medical supplies and medical supplies we'll call that one X, and water. And in this case, it says how many of each. We're looking for numbers of kits or numbers of units. So the number of medical kits and the number of water containers. So I'm going to have water containers, medical supplies. I'm going to put in parentheses kits, the number of medical kits. So those are the numbers that we are trying to find. How many of each? How many medical kits? How many water containers? Now we define our inequalities. These are the parameters. One thing that should hopefully be fairly obvious is we cannot have negative numbers of these items. So x and y both need to be greater than or equal to 0. That defines the left and bottom part of our feasible region. Now let's consider what constraints we have. The plane has a certain weight limit and it has a certain volume limit. So let's consider weight. And volume separately. So let's consider weight. Each medical kit weighs 10 pounds, which means if I have X medical kits, their weight is going to be 10 times X. We're also carrying water. The plane's also carrying water, and each water container is 20 pounds. So 20 times Y should be how much those weigh. The maximum we have is that it can carry is 80,000 pounds, so they need to be less than or equal to 80,000. So that is our weight constraint. Now let's look at our volume constraint. Each medical kit is 1 cubic foot, and there are X number of them, and each container of water is also 1 cubic foot, and there are Y numbers of those. And the maximum that the plane can hold is 6,000 cubic feet. So it has to be, the total of those two has to be less than or equal to 6,000. 6,000. Now what I'm going to do is go to a separate screen and graph all of these inequalities on the same graph and see what our feasible region looks like. And I'm ready to graph these now. Now, x is greater than or equal to 0, and y is greater than or equal to 0. Those just are the x and y axis boundaries. So let's consider our first inequality, x plus y is less than or equal to 6,000. There are the x and y intercepts. I think we should be fairly clear on this, fairly obvious, that they are both 6,000. I'm going to make my units each thousands. So I'm going to go up to y equals 6 and over to x equals 6 and draw my graph. So that is my constraint there. And now let's look at my constraint. 10x plus 20y is less than or equal to 80,000. Now, one thing that may help a little bit, you may notice that 10 goes into all of these. So I can divide each thing by 10. And then I have 8,000 there. Well, my squares, my grid squares are all in thousands, so this should all fit nicely. So now we can do the same thing as we did before. X-intercept in this case is going to be 8,000. If I make y equals 0, and if I make x 0, then I have 2y equals 8,000, which means that my y-intercept should be 4,000. So then I can graph those by connecting those two places, where x equals 8,000 or y equals 4,000. And so this is what this graph looks like. Now, I'm going to go ahead and fill in. This is the other part of it. Basically, this region that I've shaded in here is my feasible region. Anywhere in there is what is doable under our current circumstances. So now we have the constraints all graphed, but that is not all the information that we have. We haven't the information now. We have to find a way to use it. What we're trying to do is to maximize how much can be put on each plane and maximize how many people can be served by it. Now let's have a look at the original problem now. Remember, there was one more piece of information that we don't have here, and that is that we have not considered, is that each medical kit will aid 6 people, and each container of water will serve 10 people. Now, we don't have a limit on this. We don't have a constraint on this. This is what is called our objective function. Basically, this is our objective. We are our goal is to maximize this function given the constraints that we have. So we have X medical kits. They can serve 6 people. So 6X medical kits would be needed, and 10 people can be served by the container of water. So 10Y is that. What we want to do is to be able to maximize 6x plus 10y over that feasible region, which we just graphed on our previous screen. So here what we have to do is we have to take this 6x plus 10y and maximize it over this feasible region that has been drawn. Now, one very important point to note is that the boundaries of the feasible region, that's where a maximum or minimum would happen. And each of those boundaries has a corner or a vertex. There's a vertex there, there's one right there, there's one on the x-axis, and there's one at 0, 0. Now we're trying to maximize, so we can probably guess that the 0, 0 is not going to be the one that is going to maximize things. If you notice also, we really had to draw this feasible region because there are a couple of other places, x and y intercepts, that are not actually vertices of this feasible region. If you notice here at x equals 8 and at y equals 6, those are not actual corners of anything. So what we need to do then is to figure out where those vertices are. So one of the vertices is 0, 0. Another one is this x-intercept here, which is, what is that, 6,000? And then the y is 0 there. And there's another one, I'm going to do another easy one along the y, which is going to be, what is that, 0, 4,000. And then the next one is this, where these two lines meet. And it appears to be, this graph actually turns out very nicely, it appears to be where x is 4,000 and y is 2,000. Now ordinarily I would go into a big long thing about solving those two inequalities, but if you check with our inequalities, this video is already getting long, if you check those you will see that those actually do satisfy both those inequalities. So what we would do is we would test each of these ordered pairs in 6x plus 10y and see what they equal. So I'm not going to do the calculation on the screen right now. I'm going to scoot this over a little bit so I have some room. So if we plug in 0, 0, well, if you put in 0 for both x and y, we get 0. If you put in 6,000 for x and 0 for y, I think you'll see that we get 36,000. What we're looking for is which one of these is the largest. Okay, so that is bigger than 0. If we put in 0 for x and 4,000 for y, then 10 times 4,000 is 40,000. That's bigger, but is it the biggest we can get? Well, let's try our last one where we put in 4,000 for x and 2,000 for y. So 6 times 4,000 is 24,000. 10 times 2,000 is 20,000. 24,000 plus 20,000 equals 44,000. That is larger than all of the other results that we have gotten. So this is our answer. Now what this means is that we are able to send 4,000 medical kits and 2,000 water containers, and if we were to do that, we would be within the weight limit of the plane and within the volume capacity of the plane, and we will be able to aid 44,000 people. And that is what will maximize the number of people that we can aid. Now, these problems can get very involved. There are a lot of moving parts to them. They have to be taken one step at a time, and you really can't skip steps on these kinds of problems. As much as you might like to, you definitely cannot skip the step of graphing the inequalities, and you may end up having to solve a system of equations as well to find one of those vertices of that feasible region. Every bit of this is important, but you will see that you can get some very useful and meaningful results, and it's something that you probably would not be able to figure out by just using your gut feeling or intuition or trying to do calculations in your head. This is where math can get super, super practical. So that's all the time. This has already gotten to be a very long video. I would encourage you to go through this multiple times patiently. I will also try and do some more videos like this because they can take a variety of forms. So this is the first, and I apologize for the length of this video. Once I got going, I didn't see how I could stop. So please have a look at this video, and I hope that this helps.